All right, so we've been talking about our unsaturated hydrocarbons like our alkene, and today I want to talk about a possible result of unsaturation. So let's look at the Lewis structures of, or two different Lewis structures. And our question is, are these structural isomers? Are they the same compound, or are they something else? So I can see that they would have the same chemical formula, but they have the same connectivity. You know, this carbon is connected to the same things as this one. So our real question is, are they the exact same thing, like just the way I've drawn it, or are they truly isomers of each other? So a good way to do this is to build a model kit. So here I have kind of like this one right here, and then I also have the other, and I'm going to try to turn this one, I guess really be that, the way I've drawn it. So you can see these are not isomers of each other. I'm going to try to turn that into that. And what I notice is I can't. I don't have an ability to spin, freely rotate this to make this green ball here to move down to the side. So that tells me they're geometric isomers. Geometric isomers have the same chemical formula. They have the same connectivity. The things are connected to the exact same other kinds of things, but due to a lack of free rotation, they have a different spatial arrangement, different three-dimensional arrangement. And we saw that with our cycloalkanes. This is due to the fact that double bonds are rigid, because the orbitals, the way double bonds are created, we don't end up having the free rotation that we see in a single bond. That makes these two positions not equivalent. If you are above the double bond when the molecule is formed, you cannot then be moved to the bottom side without, like, you can flip the molecule over, but that flips the other side too. So in reference to the other side, if you're both on the same side when the molecule forms, you're stuck that way. You cannot have one flip and get to the bottom. So, and one thing to note, sorry, kind of forgot to say this, the two things that we're comparing off of it do have to be different from each other. So I have green and white. If I have white and white, for example, on this one, these two spots do become equivalent because of that free rotation. Not the free rotation, the ability to flip in space. So we need to reflect this in our naming. So we have cis 1,2-dichloroethane and trans 1,2-dichloroethane. So really identical overall IUPAC names, except this little clarification in the beginning. And I want to talk, these really are totally different structures because they have different properties. So for example, looking at a different geometric isomerism pair, so cis and trans 2-butene, both are 2-butene. They're both 4 carbons long, and they have the double bond in the second spot. Having the double bond in different spots would make you a structural isomer because it would change your connectivity. The double bond's in the same spot, but we have the double bond with the parent chain on the same side, continuing on the same side. And here our groups are on opposite sides when they're formed. Look at their boiling points especially. Now that might not seem like a significant difference, but it's different. They're not the same substance. This would be enough of a difference to allow us to use boiling points to separate them. If I had them all in one container, I would be able to heat that solution up, and this trans 2-butene would boil off first. The minute my thing had heated up to 0.9 degrees Celsius, it would begin to boil, and I would be able to collect that off. So they're different substances and therefore deserve different names. You've probably heard of cis-trans isomerism before, not just in this class. Sorry, my PowerPoint's having issues, but through cis and trans fats. The majority of natural occurring fats and oils are cis. They have this, if they have a double bond, the parent chain ends up on the same side of that double bond. So in this case, it's like this is above, so this is a cis fat. And trans fats do exist in nature to a very, very tiny degree. Mostly they are actually a product of the hydrogenation of fats. We're going to be talking about hydrogenation in the near future, but essentially we like to saturate these with hydrogen so that we don't have a double bond anymore. And a byproduct of that is the double bond reforming, but maybe not necessarily in the exact same way. And so we get trans fats as this byproduct. that is mixed in with our fat. So here we have, it's a little hard to see, you have to kind of look. Here, our parent chain kind of below and then continues on above. And trans fats we know are linked to heart disease, so you're recommended to limit your trans fats. And when we say that, we are talking about essentially a geometric portion of the molecule. We want to limit the kind of fats that have this. Because they're not as natural, our body doesn't seem to process them the same way, and they lead to more problems. So identifying cis and trans isomers. So we're going to decide whether each compound is cis, trans, or neither. I'd encourage you to pause the video for a second and go ahead and try right now. Now, these are a little bit challenging, so we're going to come back to this after we learn some tips and tricks for identifying cis and trans isomers, because we have a lot of things going on there. Do we look at the chlorine or do we look at the carbon, and how do we follow? So we're going to use this structure right here as our base point. The first thing you want to do is look at what comes off of each of these carbons. And the reason that's important is that if these are the same, geometric isomerism isn't possible, and that's for either side. You just need to have one carbon have the same things off of it, and those two spots are now equivalent, and there's no cis and trans, it's just that one structure. And make sure that when you do this, you're comparing this to this and this to this, and not crossing. We're comparing these two together to each other and comparing these two together. Now when I look at them, I can see that they are different groups. This CH3 is different than the chlorine. This chlorine is different than this little ethyl group. So both carbons have to be different. After you do that, the preference is really giving to tracking the parent chain, the whole carbon chain. So compare the locations of the other carbon atoms. Now you might have to do substituents. Maybe there aren't other carbon atoms, in which case, look at your chlorines. But we have, here's our parent chain, 1, 2, 3, 4, 5. Compare the locations of the other carbon atoms in the parent chain to the location of the double bond. If the parent chain runs on the same side, it's cis, and if it runs on opposite sides, it's trans. So this is what I mean here. Here I have my little one carbon group that starts this little pentene here. So this is the first carbon, and I go, it's below. So below, and then it goes above. So I went from below to above. So those are on opposite sides. So therefore, when I go to name this, I'm going to reflect that it's a trans 2,3-dichloro-2-pentene. So these are on the same side, but we're actually going to focus on the parent chain. The parent chain begins below and ends above. Above and below are different, so they're opposite each other. So then going back to those, let's apply that knowledge here. And again, if you haven't already, pause the video and solve them, applying that rule, and then check your answers with the rest of the video. So starting with this one, I would name this cis. We're not worrying about naming. These are probably more complicated names than you'd ever see anyway. So just focus on the geometric isomerism. This is cis because here my parent chain is 1, 2, 3, 4, 5. If I go this way, it's only 4, so that's not my parent chain. So it starts above, and it stays above. Above, above, same. Down here, cis as well. Parent chain begins above, stays above. Or if it had began below and stayed below, or went back down below. Now this one here is a little bit more challenging, and you really have to pay attention to that very first thing that we looked at, because this is neither. It cannot have cis and trans isomerism. And the reason is, when I look at this structure here is identical to this structure there. So as if you have two off the same carbon that are the same, those two spots become equivalent, and there isn't a cis and trans. Or if you built a cis and your friend built a trans, you've actually built the exact same structure. So really quickly, what about alkynes? Do we need to worry about cis and trans isomerism with alkynes? Well, thankfully, no. And it has to do with that geometric nature that the triple bond generates. You guys might remember from the modeling lab that our alkynes are very linear. That triple bond creates a very linear structure where the substituent goes straight out. So you cannot be above or below. There's no three-dimensional space issue. And anything off of this is very likely to be a single bond and then can rotate from there. So alkynes cannot exhibit geometric isomerism unless they're cyclic or unless they also have a double bond. But the triple bond itself doesn't create isomerism in that capacity. Can create structural, of course. So finally, just in summary, what I'd encourage you to do here as well is to pause the video and write your own summary and then compare. This is a form of retrieval practice. Make your brain retrieve it and then compare it either to your notes or to the 4 bullets that I have here. So in summary, like cycloalkanes, alkenes may display geometric isomerism. May. Not every alkene nor every cycloalkane has a cis and trans version. This is due to the lack of free rotation around the double bond. So cycloalkanes lose free rotation because the ring locks. The double bond, due to the nature of the pi bonds that generate it, lose free rotation as well. And so if you're both on the same side of the double bond when the molecule is formed, you're staying on the same side together. The groups of each carbon atom in the double bond or off the double bond have to be different from each other in order for geometric isomerism to be possible, in order for there to be a cis version of that molecule and a trans version. These are different substances, they do have different physical properties, and therefore they deserve different names reflected by the cis-trans. And then finally, in terms of naming, follow the parent carbon chain to determine if it's cis or trans. Now it might not, maybe it doesn't, like our very first one, that dichloroethane. The 2 carbons were the double bond. And then you are going to look at things like halogens and off of that. But beyond that, we're focusing, and this is so we're all naming things the same way, we're focusing on the parent chain. If the parent chain starts above and then goes below after, we're going to name that a trans alkene. All right. If you guys have any questions, let me know, and I hope to see you soon.